Now let's start section 3. It's about DC operating point. So it includes 3 lectures, 8, 9, and 10. It's about DC operating point, DC sweep, and the DC transfer function. First, let's talk about the DC operating points in lecture 8. So what is DC operating point of a SPICE simulation? Usually, it is a DC solution of a circuit. This circuit consists of different components which its own current versus voltage, also known as IV characteristics. When we perform a DC operating point solution, for example, the capacitor will be open and the inductor will be short. Why? The reason has been discussed in previous lectures, so let's just briefly discuss here. The impedance of a capacitor ZC is 1 over SC. At DC operating point, that means S equals to 0 and impedance of a capacitor is infinity. So it becomes an open circuit. On the right hand side, we have an inductor. The impedance is S times L. At DC operating point, S equals to 0 and impedance of inductor becomes 0. It is like a short. By doing this, we can ignore the existence of capacitor and inductor in the circuit and do the DC operating point solution. As a result, the output data will be given as a list of node voltage and the loop current as the solution. So in LTspice, you can go to simulate and then edit simulation command. In this window, you can choose the DC operating point. The syntax is .op. A few more things. First, the DC operating point is about a static simulation when time t equals to 0. After simulation, the operating points of the circuit will appear in a dialog box. Also, you can move your mouse to a node or component to check its voltage, current, and power dissipation, which is very helpful. In this example, it is a voltage divider with RC filter, has been shown before. The DC operating point is found at time t equals to 0. The syntax uses .op. The initial condition in this case is defined as .ic Vsense equals to 3 volt at t equals to 0. We know that this is a pulse given at 1 milliseconds, so at time equals to 0, V1 is 0 volt. After you run the simulation, this dialog box will pop up and gives the voltage at Vin, which is 0, and Vsense, which is 3 volt as the initial condition. The current as over C1 is pretty small, which is approximately 0. Current into R2 is 3 volt over 10K, and the current into R1 is minus 33 microamps. Because we have 3 volts here and 90K here, the current is flowing from bottom to the top of R1, so it is negative. It's very interesting to see the capacitor current is found as 3 to the minus 21 amps, which is very small. So by using 3 volts, we can imply that under operating condition, it means under DC operating condition, the DC impedance of C1 is 10 to the power of 21st. Also, you can move your mouse to a node or component. If you move your mouse here, you can show the DC operating points as 3 volt. If you move your mouse to a component, you can see the current over this component and also the power dissipation. This is the second example. We have a voltage source, 5 volt, has series resistance as 10 ohm, and this voltage source is in parallel with a diode. In this case, we have 2 different IV characteristics. This red line is for this voltage source with 10 ohm series resistor. The blue line, which is nonlinear, gives the IV characteristic of a diode. In this case, the DC solution is simply the intersection of these two IV characteristics. And LTspice gives the operating point as shown here. This is going to be the solution for these two IV curves. You can see that in this case, because voltage V2 is providing power, so the current from V2 is negative. If the current is positive, as in the previous example, that means this voltage source is dissipating power. This is the third example. In this example, we want to find the IV characteristic of a Schottky diode using the DC operating points and steps. This is a very tedious way to do the job, but the point is to show you a combination example of operating points and the steps. In this case, we define a parameter as capital X, starting from 0 volt and ending at 5 volt, and increment is 0.1 volt. This is the syntax to define a step function. The semicolon is used to start a comment. So this is just a comment in LTspice. Also, we can use the .op to find the operating condition. So in this case, if you run, there will be no pop-up dialog box. There are two purposes of the parameter X. First, we change the voltage here from 0 to 5 volt at a step of 0.1 volt. The second purpose is we can have a index parameter X to cycle the operating points runs. So let's see the results. Once you run the simulation, this plot window will pop up. And if you right-click on the x-axis, you can define the x-axis as the voltage over the anode. You can define the voltage here. Also, you can add a trace as ID1, which is the current over diode D1. By doing so, this figure gives the current versus voltage characteristic of a Schottky diode 1N5817. However, this diode current is limited by R3, which is 1 kilo ohm, so that because we only have 5 volt voltage source, the maximum current from the voltage source is only limited by 5 milliamp. Of course, there's a better way to get the IV characteristic. That is using called DC sweep. It will be discussed in the next lecture. Another tip is you can save the plot setting as a file extension .plt. Once you save it in the same directory, for every time you run the simulation, the same plot will be shown automatically, so which is very convenient for your simulation. There are different methods to estimate the DC operating points. It could be Newton-Raphson iteration or other methods. If the Newton-Raphson iteration fails, LTspice will switch to other choices as listed here. The left column shows 4 different methods, and the right column shows the SPICE directive to disable them. These are the reference for this topic. It's all done for this lecture. Thank you very much.